Hello everyone. Today I'm gonna start a new tutorial series on 2D flood modeling using HEC-RAS. Uh, the latest version of the HEC-RAS is better, but if you want to use any previous version, that is also okay. But we need to have our latest RAS mapper that helps to generate the mesh and to develop the model. So first, let's find out the study area. So I didn't even fix any study area here. I just downloaded the NASD plus subbasins. You can see we have HEC-12 subbasins. And if you want to download this entire shape file, you can go there. Let me show you where did I get it. So if you go to just EPA website or USGS, you can just search for NASD plus dataset, and it will give you the option to select the region if it is within Texas, and it has even several regions as well. So what I have done, I just selected 12, and from there you can see like a list of dataset. But what we just need to download the shapefile of the subbasins we just saw, and also we need to download the shapefile of the streams. So those are already delineated. So what we have to do, we just need to download this one and this one. So I have already created a file by this name. So the folder I created called HEC-RAS 2D. And then I have one folder here as GIS files. All the GIS files and project will be saved here. So I have saved those NHD plus dataset. Then I unzipped it. And then you can see we have the shapefile inside this folder. And here I created a GIS project using ArcGIS Pro, because this ArcGIS Pro is the latest version and we can use the Python 3. And yeah, this is how we'll utilize the functionality of ArcGIS Pro, and we'll automate some processes there. So that's that. I just added this to here on ArcGIS Pro, and you can see it's within Texas. So out of this, we need to just select one HEC-8. It's basically hydrologic unit code. It has a 8-digit code. So if I just select one area, this is HEC-12. And if I open my attribute table, and I can see which one is that, like if I turn on this one, or if I already exported that. So let me turn on that attribute table, and here we can see that's the HEC-8. So if I copy this, so that's the common for different. So this is HEC-10 naming, and this is HEC-12. So there will be different HEC-12s. I don't know how many HEC-12s we had previously, but now we can see there are many. So this is the version 2 NHD plus dataset. This is basically the latest one. So let me just copy this one and search for this data here within this big file. If you go there, you can see the entire list. There are many, 4,158 like subbasin within this dataset I downloaded for Texas region 12. And I'll just search for HEC-8 here. So select by attributes, and then it's already there, HEC-8 equal to this. And then if you just apply, it will select how many HEC-8, like HEC-12 you have within this HEC-8. So it's 34. So what we'll do, I'll export these subbasins or subwatersheds, and we'll process our rainfall input for this one. So what we'll do, usually we'll just select one smaller area to make it more efficient, because if you develop the model and generate the mesh for the entire HEC-8, it will be huge. It will be several million cells, and your computational time will be very, very high. So in order to reduce the computational time and to make it simple, we'll just select one HEC-12, and I'll show you how to generate the input data. But I'll generate the input file for the entire HEC-8, and you can just use the same rainfall data infiltration data set for any of the study area within this HEC-8. So this is how we develop the model for HEC-8. And if you develop one model for this HEC-12 or HEC-10, whatever it is, and if you have separate model, then we can connect the model because we have flow from upstream. So this flow is basically inflow to this study area. So we just use a tie-in to connect this all the models, and we submit one report or one flood map for HEC-8. So what we can do, what I have done here, just I was exploring and I selected this HEC-12 and I just exported it. But here I'm just trying to export all the HEC-12 that we just selected. And based on this, I'll show you how to process the input data set, especially the rainfall data. So we'll use frequency storm. We'll download the data for 2-year return period, 10-year, 5-year, 25, 50, 100, 200, 500, and 1,000 year of return period. And at the same time, we have to even generate plus minus 1%. 1% means 100-year return period of any flood event. So there are some guidelines like to generate that plus minus profile as well. Plus minus 1%, we need to download those data set. I'll show you just after a few moments, and then we'll see what I'm talking about. So first, export, right click on that since we already selected, go to data set, and then export the feature, and then select where do you want to save. I have created one directory there within GIS files as chef files, because here I'm gonna just select all the chef files I have. I can use that HEC-8 ID. So that's the HEC-8. I can even use the name as this HEC-8. We know it's HEC-8, and that's the ID of the HEC-8, and then SSP. So let me just export it. Yeah, we have exported basically. Let me turn it off. I'm turning it off as well. And then I'm just deselecting everything we have. So that's the HEC-8. It contains even how many? HEC-12, 34, right? But out of this 34, we'll focus on this HEC-12. So what we have to do first, we have to select the projection system, because this data, it's not in local state plane projection or UTM. So if you just right click on that and go to properties and then sources and spatial reference, you can see it's basically 4269. It's in degree minute. So we need to convert it to US feet. So how can you make sure that, okay, this is the location? Because within USA, there are different projection system, and based on different region, we have different IDs as well. So we need to download another chef file. So here, if you just download, because you need to know all these steps. So here, you can download the projection zone. So I'll give you the link in the description below, and you can just click on this, and definitely you can practice from those links. So if you just click on those shape files, it will download these shape files. And if you just import it into GIS, that's what I have done here. So you can see the zone number, Texas Central 4203. So our study area is basically, we have different one here. That's the boundary. If your study area is falling under this zone, then you have to use this Texas South Central 4204. But here we're using Texas Central 4203. So we have to find out this projection system, and we have to project this subbasin. So let's go to geoprocessing and go to projection and transformation, and then project, double click on it and select this HEC-8, the one we just exported. And then here, that's the name of the file, means definitely it's gonna save you can see the location. It's showing a different location, but I want to save everything inside my chef file. So let's go to our JS folder inside chef file. I'm copying the location, and here I'm pasting the location to directly go to that. And here I just want to make it like based on the zone number 4203. So that's the FIPS projection zone state plane. I'm saving it and then assign that projection here. So how can you find it? If you click on the globe sign, you can go to project, TED coordinate system, and then from there you can find out state plane here and then find out US feet. Usually we'll use NAD 1983 or 2011. So let me find it out. So US feet, you can expand it and you can see state plane for different region, California, all the states are there. Find out Texas, and you can find out different zones. So Texas Central, it's South Central. We need to use Central 4302 or 42. We need to find out 4203, right? 4203. So that's 4201. So that is basically 4203. See, Texas Central, and it's in feet. And if you want to save it, you can just right click on it and you can save as projection, because we need to save the same projection for RAS mapper as well. So I already saved it. You can just save as projection file and you can save it as a different name, but later on we need to use that. So you can just add this to your favorite. So later on you can just directly use it from the list of your favorites. So I'm just clicking OK. And then if I hit that button run here, then definitely you can see. Let me remove my picture there. So I'm clicking on run. It's almost done. Yeah, it's done. So I'm turning it off. I basically don't need that. I'm removing that. If I right click to check, go to properties, and now go to spatial reference, you can see it's basically NAD 1983, right? It's 2011 and state plane and Texas Central FIPS 4203. So I have this projection here, and if you want, you can make it hollow as well. If you want, you can just change the boundary color to red if you want. That's what I do. So that's it. So that is our projection zone. And if you want to add any imagery, you can go to base map, and from there you can add imagery or hybrid, whatever you want. So that's that. So out of this HEC-8, we have our study area there. So that's what I did. Like this one is my study area. So we'll set up the HEC-RAS 2D model for this boundary, but we'll process our inputs for this entire HEC-8. I have already projected that HEC-8, and now I need to download the rainfall data. So what I have to do, I'm just going back to this folder inside models. I have two different folders. One is hydraulics. Here we all set up, it's empty now. We'll set up our HEC-RAS 2D model, and within hydrology, because we need to process like loss factors, infiltration, we need to use Manning's calibration zone, and we need to find out the values based on land use and land cover. We'll do that. And so let me just delete whatever I have here inside hydrology, because I just processed this data set previously. So I'm just trying to show you everything from HEC-RAS. Okay, I can delete. Okay, let me just show you a script. I have a script to process everything. That's okay. I'm going back to hydrology. So within this Atlas 14 frequency storm precipitation, right? You can see I have different profiles. So here, what I'm gonna do, I'm gonna delete everything. And then I have to download what I'm talking about. Let me show you that. If you just look for Atlas 14 frequency precipitation estimates, And then I'll give you the link in the description and you can find out. And there are different zones. So you can see if it's Texas, it's 11. And here you have to select the limit. First, we'll use this precipitation frequency estimates without any upper or lower limit. And you can use partial duration series, or you can use annual maximum series. So most of the cases we use this one, and we use other one as well. So here we have the recurrence interval. 1% means 100-year return period. And here we have the duration, means the accumulation period. So we are gonna use this 24-hour accumulation. So if you have rainfall, and if you sum all the rainfall values within 24 hours, means 1 day, and then you can process this data. And if you project it based on its recurrence interval, so we'll have all this from 1 year to 1,000 year. So first we'll start from 2 year. We don't need the yearly interval. So 2-year return period of a rainfall. We'll just download this as a raster, means as ASCII raster, because we want to use gridded precipitation. That's why. So this is basically 50% chance in a year to occur. So that's 2-year return period. And if you just click on download to begin, so it will just ask you where to save. So I'm saving everything inside this, and it will save as this Texas 2-year 24-hour. Okay. And then it will save as .zip file. That's okay. I'm saving this one, and then change the period to 5. Click here, just download everything one by one, and then 10-year return period. So this, and then go to 25, click and save, then go to 50, click and save, then go to 100, click and save, go to 200, click and save, go to 500, and then click and save again, and we have 1,000. So other than these profiles, we need to even generate other 2 profiles. We call it 1% plus and 1% minus. Means if you have 100-year return period, we call it 1% chance of occurring in a year. So we need to just generate 2 other profiles based on different method we have. So we need to calculate 90% plus and like upper 90%, lower 90%. So here we need to change this to upper confidence limit and select 100, and then click and save, and then lower confidence limit only for 100, not for other. Click and save, and let's check what we have here. So inside this, maybe it's still saving. So we have all the profiles starting from 2-year to 1,000 year, right? And then we have extra 2 profiles, upper limit and lower limit. So L means lower, U means upper, and we also have 100. So we'll utilize this 100 as median, right? 100 as median, upper and lower as the upper and lower limit to calculate 1% plus and 1% minus. So I have written a Python script that can basically convert these rasters into 6-minute interval, because these are the rasters, only one value within 24 hours, but we need to distribute that. And we need to use the distribution factor to distribute it. So what we can do, we can basically test what we have here. Let me just try to unzip one. So, okay, let me just copy one, and I'm just trying to paste it here to demonstrate what is there inside, because I don't want to toss anything inside this folder. I'm just trying to unzip, and here we have the raster, and let me just open it in GIS, and you can see what is going on as a raster file. And if I just open, and you can see it's basically covering the entire Texas probably. Let me just allow some time to load. Yeah, see, it's basically covering the entire Texas, but our study area is here. So I don't want to process everything for Texas, because it'll occupy huge amount of data sets, like your space. We don't want to do that. So instead of doing that, what we'll do, we'll just clip it. We'll use a buffer area of buffer, basically length. So we'll extend as 5 mile everywhere, and we'll just clip it. But here you can see we have only one value for 100 here, and we have the same scenario for other profiles we just downloaded, but we need to run the model. So if you use this one single value, so we won't get the distribution. So we have in our CS a temporal distribution factor. We'll apply that factor to generate a 6-minute interval raster from this one single raster for each of the profiles we have here. So let me turn it off. We have this study area, and I have downloaded and collected this temporal distribution. If I turn it on, you can see it's basically showing Texas A, Texas B, Texas C, Texas D, whatever it is. It's showing basically different zones. You can see the polygon, right? So for this study area, it's falling under Texas A, Texas B, Texas, yeah, A and B. So what we need to do, we need to check the temporal distribution for this Texas A, Texas B, or Texas C. So I have this data set, like, let me show you here. So in our CS distribution, if I open the Excel file, you can see we have time here, like 6-minute interval. And for different zones, you can see for Texas A, B, C as well. So here, so within 24 hours, we need to just distribute that rainfall at 6-minute interval using this. If it is falling under Texas A, so we'll use this factor to multiply the rainfall value for each of the grid in the ASCII data set we just saw. If it is within B, so we'll do that. If it is falling under A and B, then we need to take the average, and then we'll apply the distribution factor to distribute it. So let me close that, and let me show you it's falling under Texas A and Texas B. So you don't need to worry about where it is. You just need to use this shapefile. You need to use your study area shapefile, and you just need to use the Excel file as just showed you. So I have written a script that will automatically intersect and find out the zone. If it is falling under one zone, A or B or C, whatever it is, even for other location as well, it doesn't matter. So it will just automatically apply the temporal distribution to produce 6-minute interval of raster. So it will be clear to you whenever I'll just demonstrate. And in order to do that, you need to collect this shapefile, your study area shapefile, everything, and then we can even produce our DSS file. So we'll process everything. We have different profiles. How many profiles we have? We see, okay, let me go inside this. I don't need that. I have everything here. So we have basically 11 profile, right? 11 profiles. So out of this 11, we have upper limit of 100, lower limit of 100. So we just need to generate plus minus 1%. But we don't need the upper limit and lower limit for our flood modeling. We'll utilize those values to produce plus minus 1%. So how can we do that? I've written Python script that can generate plus minus 1%. So in the next video, I'll show you how to generate the gridded precipitation input for HEC-RAS 2D flood modeling. So we have to include all the profiles, because in real world case, we utilize all the profiles, especially 10-year, 25-year, 50, 100, 200, and 500 with including plus minus 1%. So I'll just show you in the next video, and then I'll start processing soil data, land use data, and also I'll show you how to calculate that gridded curve number, and also how to generate the 2D mesh, how to run the model, how to calibrate the model, how to refine the mesh where we need to. So at the end, I'll show you how to generate the flood inundation map for 100-year return period and 500-year return period, because these are the two profiles we care about most. So in the next video, I'll just show you my script. I've written a script that can automatically process and generate the DSS. So that's all. If you have any question, you can practice the same way I just demonstrated to select any study area, because this time I'm not gonna upload all the files because I don't have any space on my either Google Drive or Dropbox. That's why I got a lot of comments that, okay, people are not able to access those data set, and I don't usually save those data. So this time I'll just show you everything from scratch, how to download this data so that you can easily download and practice and you can replicate. So that's that. If you have any question, you can just put your comment and I'll try to answer that. So that's it for the first part. And in the second part, I'll show you how to generate .dss file. So until then, it's okay. Take care.